All right, everyone, we had 3 bits of homework last night. The first one was page 761 and 3 to 9. Any issues with 1 or 3 to 9? Wilson? 4? 4, 7, 11? 4, 7, and 9? I get 4, 7, 9, number 1? 1, 4, 7, 9? Okay, 1, 3, 4, 7, 9. Question number 1, then, everyone. It says an electron moving at 5.0 times 10 to the, get cut off there. I think that's 10 to the 5, is that right? 10 to the 5 meters per second, enters a magnetic field of magnitude 100 millitesla. Circle that because non-standard units. What's the max force that the magnetic field can exert on the electron, and what's the minimum force? This isn't even really a cathode ray tube question, right? It's more of just a magnetic fields and forces question 2 units ago. That's okay. It's a good order review for us, and since we use magnetism in this unit quite a little bit with the cathode ray tube, it's not a bad idea to go back and review that stuff. What's the max force and the min force? We said way back in Unit 3, when we looked at magnetic fields and forces, the magnetic force on a moving charge was QVB. If what? What's the big if? That equation is valid for the magnetic force on a charge moving through a magnetic field if what? The equation didn't look exactly like this, actually. The equation really looks like this. Michaela, what's the big if? Yeah, if the charged particle is moving perpendicular to the field, right? That's the little upside down T there. If the speed of the particle is perpendicular to the magnetic field. If the magnetic field is parallel to the way the particle is moving, then what's the value of the magnetic force? You guys remember that one? No. 0. All right, we can answer question B there pretty quick then. What's the minimum force? It doesn't get any smaller than 0, right? The minimum force acting on a charged particle moving through a magnetic field is 0 newtons if the particle is moving parallel to the field. What's the maximum force? Whatever this is. If they're perpendicular, that gives us the maximum force. If they're parallel, that gives us the minimum force of 0. So I don't know exactly what the value is there, but it's a pretty straightforward question as long as you realize that that's the equation that we use to solve it, right? Q 1.6 times 10 to the minus 19 times 5 times 10 to the 5 times 100 times 10 to the minus 3 Tesla gives us our answer. Is that okay? Let's get 3. What experimental results led Thomson to conclude that all cathode rays consist of identical particles? That's a good question, because I don't think that when we went over the cathode ray tube that we actually addressed that question per se. So you might have to kind of read between the lines here a little bit, give a little bit of thought to this. What experimental result led Thomson to conclude that all cathode rays consist of identical particles? What do you think it is? What told him that they were subatomic particles? The charge to mass ratio, how big it was, right? Carolyn, what told him that they were identical particles? Be careful. No, be careful. That's Millikan's oil drop experiment. The oil drop experiment told us that we had an elementary charge and that we had charge quantization. Okay? This is Thomson, the cathode ray tube. So Thomson never found the charge. He had no idea what the charge of the electron was. But he did know, Chase, he did know the charge to mass ratio. And if we find the charge to mass ratio of all of those particles is 1.76 times 10 to the 11 coulombs per kilogram, if the charge to mass ratio of all of them is the same, then the logical conclusion from that is that the particles are the same. Number 4 says a beam of electrons enters a vacuum chamber that has 100 kilonewton per coulomb electric field and a 0.250 magnetic field. So right away I see this, I'm starting to think what? Electric field and magnetic field together, I'm starting to think velocity selection chamber of the cathode ray tube. We want to find, first of all, we want to draw a picture of the electromagnetic fields that will cause the electrons to go undeflected. And then we want to find the speed at which they'll go undeflected. So let's draw the particle here first. It's a beam of electrons going to the right. Let's say we have a magnetic field pointing into the page. If there's a magnetic field pointing into the page, there's going to be a magnetic force acting down towards the bottom of the page. Thumb, fingers, palm points towards the bottom of the page. All right. What kind of electric force do we need to balance that magnetic force? In other words, to cause these particles to go undeflected, which way does the electric force have to point? Kim? Upwards. So we need an electric force upwards. Which way do we need our field to point, our electric field, that is, to point, in order to get an electric field force pointing upwards? Which way? Good. Downwards. If it was a positive particle, the positive particle would experience a force in the same direction as the field. A negative particle experiences a force opposite to the field. Remember we talked about that 3 units ago now, back in Unit 2. That's not a crazy hard thing, but there's a lot of not so crazy hard things that we've got to remember, right? And it's hard to remember them all. It is. That's why I've got to work hard over the next few weeks to make sure that we remember as many as possible. So we got a magnetic field into the page. We got an electric field pointing downwards. Now we could have a different answer. Anybody have a different answer for this that could think might work? What's the one other answer that we could take for this? What if the magnetic field is pointing out of the page? Could that work? If the magnetic field is pointing out of the page, could we make that work? What would have to happen if the magnetic field is pointing out of the page? What would have to happen to the electric field? It would have to point which way? Right. It would have to point upwards. So basically, the magnetic force would be upwards. We'd need the electric force to be downwards in that case. Okay. What speed would they need to pass? Would they need to move to pass undeflected through that part? Well, this is clearly the velocity selection chamber where Fe equals Fm. Don't get that mixed up with the oil drop experiment where Fe equals Fg. So let's say Q times E is equal to M times G. No, sorry. Q times E is equal to, I just said, don't get that mixed up with the oil drop experiment where Fe equals Fg. And then I wrote down QE is equal to M times G. This is what happens when you get old. QE is equal to QVB. Solve for V, I get E over B. Whatever that works out to be. I'm going to guess 10 to the 5, 10 to the 6 meters per second. 10 to the 5, was it? What was the actual number? 4 times 10 to the 5 meters per second. Okay, the typical speed is 10 to the 5, 10 to the 6, right? Good. And I think we had one more to go over here. 2 more to go over. 7 and 9. Use the appropriate hand rule to determine the direction of the magnetic field in question 6 if the protons rotate counterclockwise in the same plane as this page. So here's my proton. Here it's rotating counterclockwise. Which way do we need the magnetic field to point in order to cause that to happen? Well, at this point, at the top here, okay, the particle is moving to the left. So I'm going to take my right hand, it's positive particle, right hand rule for deflection, thumb to the left, palm points downward, because we know at that point the magnetic force has to point downwards. It has to, otherwise the particle is not going to be deflected downwards like that. Right thumb to the left. Palm points downwards, fingers point into the plane of the page. So the direction of the magnetic field must be into the page. Again, not really a cathode ray tube problem, more of a magnetism question, but good little review for us. And finally, with this set at least, finally, question number 9. I like this question. I like this question a lot. Calculate the net force acting on the particle. I don't know about you guys, but when I read through this at first, I started thinking velocity selection chamber, right? Electric fields and magnetic fields together. The problem is they're not telling me that they're balancing, and they're not telling me they're going through undeflected, right? What's the net force? If the net force is 0, and it could be, then they'll go through undeflected. But if the net force isn't 0, then it won't go through undeflected. Okay, let's figure it out. Let's look at the magnetic force first. Okay, right-hand rule, because it's a positive particle. Thumb in the direction of the particle. Right fingers in the direction of the field out of the page. Palm points downwards. The magnetic force acting on this particle is downwards. What about the electric force? Positive particle, the electric field downward, the electric force will be which way? No, not out of the page. Electric field. No hand rules here. Okay? Hand rules are for magnetic fields. Which way is it going to be? Downwards. Okay? Positive particles experience a force in the same direction as the electric field. So both of them are downward. Are they ever going to balance each other out here? No, they will not. It's impossible to balance because we get two forces in the same direction. Okay, let's figure out what the net force is. Let's say F net is equal to Fm plus Fg, Fe, I should say. QVB plus Q times E. Can I cancel out the Q's there? No. Because they appear in every term on the right side, but not on the left side. One times 10 to the 5 is the speed, and B is 0.50. E was, what was that, 100 newtons per coulomb? Both of these terms should be negative because the forces are downwards. Negative 8.0 times 10 to the 15, make 15. Is that right? Is that right? Subtract 1.6 times 10 to the neg 17. So our net force is 8.016 times 10 to the 15 downward. Now, my favorite part of this question is B. Will the net force change over time? And explain. Who's got an answer for that? Who thinks they have an answer, at least for that one? Who says yes, it will change? Who says no, it will not change? Okay, so nobody raised their hand for yes. Two people raised their hand for no. Caden, why do you think it'll change? Will it speed up? If there is a net force, two forces acting downwards, you're going to cause a change in speed of the particle. It's not a constant speed. It will speed up. Right? It will. If I throw this pen right now, it will speed up as it falls towards the floor. Now, this isn't a perfect parabola. It's going to go in a circle as a result of the magnetic field, a parabola as a result of the electric field. So it's some kind of combination between a parabola and a circle. I don't know what that shape is, but it's going to speed up. So it speeds up. That's going to change the value of the electric field, and that's going to change the value of the net force. Sorry, it's going to change the value of the electric force, which is going to change the value of the net force. But it's also because as it goes down like this, the electric force, sorry, the magnetic force starts pointing in different directions. So not only is the value of the electric force changing, but the direction of the magnetic force is also changing. So both of those lead you to a net force that's going to be changing, right? So the one of you who guessed yes is right. You just didn't give it to me, though. You just didn't give me your semi-viable stuff.
Yeah, I said I thought it would speed up.
Well, yeah, but you didn't back it up. You said you had stuff to back it up with. Oh, okay. All right. We had some questions on 763 as well. These were Millikan's oil drop experiment where we had a charged particle suspended, an oil drop suspended. Okay, 764, it's when they were accelerating. Any questions on 763? Like maybe question 2? Let's do question 2. Let's do question 2. All right. I'm going to tell you guys the same thing as I told the class this morning. Okay? I've taught Physics 30 for 19 years. Okay? You guys are smart. If you guys think you know more about electric fields and magnetic fields than I do, you're wrong. It's not because I'm smarter than you. It's because I've taught it for 19 years. Okay? I could be dumb and still know more than you guys after 19 years of doing it. I've got to internalize something, right? After 19 years. Trust me on this. Whenever you're dealing with trying to find a sign of a charge or an electric field direction or something like that in a Millikan oil drop experiment, draw the picture. I know some of you are not going to follow my advice, and some of you are going to get a question wrong on a diploma exam because you think you're smarter than I am. Okay, listen, if you don't care if you get a question right, then do whatever you want. If you want to get it right, then follow my advice. Draw the picture. We have an oil drop that's suspended. If it's suspended, that must mean the electric force is upwards and the gravitational force is downwards. How's that helpful to me? Well, we first want to find the value of the electric field. Fe equals Fg. We say Q times E is equal to M times G. Becomes mg over E. Okay? Not a crazy hard question mathematically to solve. We end up getting 9.8 times 10 to the 5 newtons per coulomb. All right, how do we know that the electric field is up? This is where my diagram comes into play. Some of you may be able to think about this in your head and sometimes get it right. But when you draw the picture, you're almost always going to get it right because it's literally staring you in the face. We have a positive particle that experiences an electric force upward. Which way does an electric field have to be to cause an electric force upward? Upwards. Right? The electric field and the electric force are always in the same direction if it's a positive. If it's a negative, which way would the field have been? Downward, opposite to the direction of the force. Got it? Okay, the diagram is helpful. Whether you think it is or not, it is, trust me. All right, that's the kind of question that we get when we're talking about the oil drop experiment forces balancing, suspended oil drops. What about the ones that are accelerating? Okay, which could mean these ones that have an electric force and a gravitational force downwards, or it could mean these ones that have a gravitational force downward and an electric force upward, but one of those forces is bigger than the other. Doesn't matter. Doesn't matter which ones we're dealing with there. In both cases, we're going to set F net equal to the sum of the forces. Notice it's Fe and Fg now, not Fe and Fm. Now at this point, you need to have directions, right? You need to have negatives and positives to plug into there once you put numbers in there. What's the best way to get the negatives right? What does 19 years of my experience tell you? Draw a picture. Draw a picture. Let's take a look at both of these questions. The reason we want to look at both of them is because the answers to both of them are wrong in the book here. If you get those answers, you made a mistake. And you made the same mistake as they made, and you'll see clearly what that mistake is in a minute here. All right, let's draw a picture here, okay? Number 1 says calculate the net force on a sphere that is negative. There's an electric field upward Let's find the net force. Well, there's a force of gravity acting downwards. Which way is the electric force acting? Downwards. When they did this answer key to this question, they assumed the electric force was upwards. Force is not upwards. The field is upward. If you made the electric force positive and the gravitational force negative, you got that answer. But that's wrong. We need to make them both negative. So we do this. But when we plug in our numbers here, they're both negative values. Negative 8 times 10 to the negative 19. That's 5 elementary charges. Times 1 times 10 to the 5. Plus negative 2 times 10 to the negative 14 times 9.81. What do we get here? Negative 8 times 1 is negative 8 times 10 to the negative 14. Subtract is that 1.962 times 10 to the negative 12? Negative 13? So there's our answer there. Negative 8.20, or negative 8.2 times 10 to the negative 14 newtons. 8.2 times 10 to the negative 14 newtons downwards. Anybody get that? Anybody get that and like, oh, hey, that's not the answer, and then change it? Okay. Sorry, it didn't even occur to me yesterday. I knew this was wrong because I've done this question before last semester, and I knew that it was wrong then. I just forgot to mention it to you yesterday. That's all. Chad?
So in the question, when it says a sphere charge negative 5, that means that it is a charge of, or is it negative charge of 5 times 10 to the
No, careful. No, be careful. Be careful. No, it doesn't mean that at all. It hasn't lost 5 electrons. That E doesn't mean electron. It means the elementary charge. The elementary charge is 1.6 times 10 to the minus 19. Negative 5 elementary charges means negative 5 times 1.6 times 10 to the minus 19. Okay. It's the equivalent of 5 electrons. All right, let's get the acceleration now. To get the acceleration, we're not going to get 14. Guys, listen, we're reversing the direction of the field. Okay, if we're reversing the direction of the field, then we've got a situation like this. Okay, electric field downward. That's going to give us, since it's a negative charge, a force upwards and a gravitational force downwards. How do we know right away when we see that picture, again, diagram, picture, how do we know that that's the wrong answer? Sorry? Yeah, listen, if you've got something that's countering gravity, you can't get a net force that's bigger than gravity. It's got to be smaller than 9.81 here. Right? If the FE was acting downwards, then we could get 14. But if it's acting upward and countering gravity, it's got to be, I don't know how much less than 9.81 it's going to be, but we know it's going to be less than 9.81. So let's say F net is equal to FE plus FG. Let's say M times A is equal to QE plus M times G. Let's say, what is M here? 2 times 10 to the negative 14 times A equals the electric force, which is upwards. We're not making that positive because the field was up here. We're making it positive because the field is down, and therefore the force is up. Gravity is going to be still negative. I think when we do that, we get something like 5.6 or 5.8 or something like that. 5.81. And I believe it's negative, isn't it? Negative 5.81 meters per second squared.